module, then A at B gives you precisely the R module B back again.
Yeah.
Because it's affine maps.
Yeah, but
If it weren't affine maps, it would just be zero.
But that's what I'm commenting, that with this audience, my course is quite almost pointless.
No, it's
I mean because I'm moving to that example.
Oh, you are? Okay,
so, yeah, but you already know all this stuff. But anyway, I keep going, and this is I think I can raise the same. This is what we call a representable cliché, right? Yeah, because it's a cliché, it's a functor from the, for instance, there are module category to sets, and it's all the information from this cliché is contained in this thing. It's represented by this object. Yeah, so that's these kind of functions that are very important. So now I'm in a position to tell you about the very important general lemma.
But wait a second. Sorry
Yes?
to interrupt you, but your suggestion was that he makes an example of a concrete B and concrete A. Shouldn't you make that before you step over to this? The only abstract?
Okay, yeah.
For me, it's just, for in case you want to see why this construction is really natural in music.
Yeah. So for example, yeah, in a sense. I take this sheet and I see what does it do on the zero model. I say, well, we think, for instance, we have line transformation. And it's a good moment to introduce the notation that's different, because I think in other contexts it's more natural to put T, right? For translation. But when they say the IT group, it's an inversion and translation, right? So and I remember that in our book on Cantor, we had to change all the exponential notation to this one I suppose in order to be more understandable. So what does I do with 0 goes to the zero. Say.
I mean, there's a mathematical reason for this x being the exponent of t, because this is the exponential rule that if you compose by two such shifting thing, then the exponent will be the sum of the exponents.
Yeah.
That's why that is chosen.
So 0 goes to some point there. So you're looking at morphism, but at the same time it looks in points of the set. So you look at all these morphisms, you resolve the whole module. Well, in this case, string, but Of course, we're keeping it simple, but of course we can construct very complicated modules, set modules or Q modules or R modules that are that have having significance. Here we are simply referring to the chromatic scale. So this would be, look at the chromatic scale. The point of the departure would be this next in particular. So
it's a pretty big conceptual step to reconceptualize an element as a map.
yeah, exactly.
From one object. I mean, that was a big step.
That is
Yeah.
going deep.
Deep, you push that.
That's
Pretty far. This was
Yes.
another nice example is tone rows, right? I mean, tone rows.
Yeah.
How does that work? Like,
Tone rows, I said,
11.
I go to C11's power of Z, which is a free modular over C, and then you have those 12 basis vectors, which are the normal ones, but 0 is also one because you are in the 5 category. So that defines a map with 11 ordered values, yes. So the Z11 to Z12 is, I mean, it's more than this, of course, because you have to have this bijection, but this is kind of the set of all those maps.
yes, and so yeah. So if, for instance, if we use instead of 0 with the set 12 itself, you got all the maps between. Well, not necessarily vertical yet. It has to be set. You can have, for instance, multiply by 0 itself. So everything goes. Then is one of those. Or you can have, for instance, I know by 2, multiply by 2 in set 12, and you will recover all the even ones, all the even tones. We map all tones to even ones. And I like that very much. And I think it's the only thing that perhaps would appeal to those advanced students that I try to take more seriously this idea in the topos of music that counterpoint has to show up as harmony, for instance, with sub-addressing. So I try to be a sub-addressing to try to recover certain highlights of the history of the counterpoint. And they're trying to see what's going on with this mathematical game. But the problem is that the very specific part that Mazzola took, is interested in that we see how these tones interact, and we finally set with this consonant that is not yet quite resolved by this, but at least I think it's a good beginning, well, in my humble opinion. So I think now we can move on to the general lemma.
But I think perhaps I'm not being picky here, but you know, this set of 0 at Z12, yes, you can say this is in bijection with Z12 as a set. And this is the starting point, that the elements of Z12 are really some special arrows. I think this is the starting point. You can say, okay, now we generalize, but the elementary fact is I think, a starting point here. I don't know.
Let's see. Because I am about to define a general address point, so I think that goes in that direction. But let's go. And let's see if I have to do a work of translation and retranslation, and let's. The category where we take all the morphisms between object A and B, of course inside that category is a set, in order to be partially correct. Then my notes are in Spanish, so I have to translate this again. here we have seen representable presheet, but not all presheets are representable, so take anyone. And then take one that is representable and see all the, here it means all the natural transformations between this functor and this functor. Perhaps we should somehow modify the notation here, but I like to think that it makes sense. It's always thought as it has sense in the proper category. So here it means natural transformations. For instance, some literature put here nat, the natural transformations. Obviously, we're thinking in another category. I think that is cumbersome. And then it turns out that there is a bijection between this and this. I think it's natural and it has some other properties, but for the moment I only interested in the fact that this set, but this collection of morphisms is in bijection with this set, right? So, and I must stress this works for any presheet. So, what happens in particular if it is a representable presheet? In particular, I'm forgetting here this, by the way. But it's something simply right, like, yeah, it's, with this, right? So all natural transformations are with this functor and the bijection with all the morphisms between A and D. So it turns out that there is a copy of the original category within the category of this presheet. So I mean, no information is lost when we make this paradigm shift of no longer paying attention just to sets or just to transformations. Everything, as far as the Phrygian prism is concerned, everything is turns out to work fine. So, in this sense, is that we can replace the original object with these presheets. But and now I want to introduce this notion of I don't know. I think again, is someone taking notes, so I can wait.
It's being recorded.
No, mind. It's better to have this gesture of taking notes. Goes to the train, just looking at the screen. May I erase now? Yeah. So, is it clear, or may I explain myself a little more because I know that it's not.
I think you could restate this in a more kind of clear, simple way, in the sense of that, you say in which bijection with A and B, it means that the morphisms from A and B are kind of essentially the same as the natural transformations between the associated presheets. And that means, particularly if you go to isomorphism classes, it means that two objects are isomorphic even only if their functors are isomorphic. And this is a very strong statement. So you needn't look at the objects anymore, but look at the functors. And if they behave well, you can infer what was true already in the old category in the synthesis.
Yeah, but when I finally understand this, or at least I understand it a little bit more, I realize why you say the functors are spaces, or are some generalization of space, because I didn't get it. Because for me, functors are transformations. So in what sense they could be spaces?
Yeah, well, you have for every argument you have a set, yes. So you have kind of a system of sets. So that's
Now I'm getting it. But I remember because I was studying the initiator theory, and you say the space is a function. The underlying. I said why? That doesn't make any sense to me. But now it makes sense.
You know, a space. Sorry, I learned that from Gabriel. You know, I said, you know, I prefer the geometric point of view in algebraic geometry. understood that these points, yes, these points are really the points of a set, of a space, yes?
Yes.
So these arrows are kind of points in an abstract space, so
Yes.
that's why.
I'm moving toward that direction. So I erase this.
One question before you finish erasing it. There was the Leonila point of view. Is to know A, you told me this, to know A is the same as knowing A from all of its perspectives.
Yes.
Yeah.
So how can we see that in the Leonila? Can we see that in the
Yes, yes.
That's one of the key points. Maybe he was going to say that, but...
Yes, the statement is that A and B are isomorphic if and only if their functors are isomorphic. What does it mean to understand A in a category? It means to determine the isomorphism class in that category, right? That's what it means to understand something in a category. It means to exhibit its isomorphism class, right? So, what does it mean to know the isomorphism class of an object? It means to know the functor, how it behaves. So, the functor from all the different, other objects targeting at that A, and that functor is telling me everything about the isomorphism class. Exactly because of Leonila, yes, the functors really are isomorphic, even only if the objects are. So, understanding the objects means understanding their functors. So understanding these systems of points, does it make sense?
As we take an object within a category and look at this morphism.
Just a remark about the last detection between morphisms in the category and morphisms in the category of chips. That is just the general embedding.
Yes.
Yes, only that. You can make an embedding of the category in the category of chips.
Yes.
There's another point of view.
Yeah, there is a copy of it.
It's basically the same thing.
Yeah. I don't want to say full and faithful. Yes. Of course, the point when we know category theory. But I'm not taking that as a prerequisite in this course. So I take an object from a category, and I call the generalized point any morphism of this kind, where S it will be called the address of the generalized point. So it says you want to understand an object within a category, you have to see it from all addresses.
Yes.
Yeah, so the wait for the things there. And this is not, well, I just only changed a little bit the naming convention, but this is in this category theory book by, I have it here.
Schubert or?
No. It's in Sexta book, Basic Category Theory. And it's available for free in AHA. And he talks about it, but he does not call addresses. Too bad, because I think the address idea is the best one to take into account. And that's why you have a point, and you can have another address, and you have a new point because you can follow the path.
Yeah,
So this kind, yeah, exactly.
It's a relative theory.
Yeah, exactly. Well, and those, as I can say, those understanding A is equivalent to understanding at A, or this is seeing it from all addresses. Right? So what was the point of the dilemma? And I don't know, let me check time. I think we're quite on time. Or not. Let me see.
So that is the perspective.
Yes.
Yeah, perfect. So it's so interesting because I have to talk about this thing, but to an audience of mathematicians, but mathematicians not familiar with category theory. rather than not conversational, with conversation like a theory. And they have only 30 minutes. But I wanted to talk about algebraic geometry precisely because Shafarich just died and it's very well posed. And once you know this viewpoint, you can transfer this exposition by Shafarich into this viewpoint, and it's quite nice. It works out very nice. But unfortunately, I have no time, and because we got a little bit late. But yeah, for instance, it's very interesting when you say, I want to see, for instance, x at c, appointed as a complex number, and defined by an ideal, right? Maximal ideal. So it works out much beautiful and better. I mean, in terms of understanding, you write this in this notation instead of using the classical algebraic geometry or Phrygian. I was in more Phrygian the facts thing, right? So, but I will not go into that. So, and now I move into counterpoint because it's another thing I want to talk about today. So, this yoga of looking at everything from all addresses, I think it works out particularly well for counterpoint because, for instance, you have this. I was planning to introduce this example now, but it's already introduced. So these are pure right? Just you think about one tone, and that's pretty much the thing, right? And then I was quite, well, not surprised, but it was nice to confirm the idea I had that in the medieval times and before, music was sung by only one person. And this person was in charge of shaping the melody, and this was the art of the capability of shaping melodies, based on the text, fixed text, religious text, unfortunately. Well, I don't know. And so they were thinking on this. Of course, there's also a gesture, and perhaps we should see what happens if we take diagrams of gestures and see what's going on. This thing, but I would say in each instant they were thinking about what's your tone. So, and you can then move to self-addressed tone. And so this would be in the affine perspective. You have something like this. So you take a U and goes to YU. Because and for instance, this has a very nice thing that for instance that you evaluating 0, it takes you to x, right? And if you evaluate it in 1, take you into y plus x. Yes, so now you can have a canvas surface. And this thing will be the integral. And it's very nice because exactly, they say, why is only singing one person? Can it be two? And of course, if there are two, they don't move from this perspective because they are essentially playing this or singing the same notes. They are still here. And someone said, let's change the viewpoint, the address, and let them to be separated by some interval. You're here now. But of course, it's not trivial to decide the distance. It has to play out well. So the first idea was to sing always in a distance of a fifth or a fourth. And that's the organum. Because these were the symphonic intervals, the fourth and the fifth. The problem is that within certain election of scales, the fourth doesn't work out well. If you begin to sing in and jumping fourth, or fourth distance, you sometimes get out of the mode, and this is undesirable. And with 50 doesn't, it is not a problem. At least in the Dasein system of Música and it's at the beginning of the problems of the fault. The fault has some kind of problem, and this is the first instance it appears. Perhaps a little bit different and in the next step of the chain, but I think there is like a philosophical lesson here of why fault it will turn out to be important. So what comes next is somewhat more speculative, but at least it has resisted the experimental tests so far. And we're also said, well, why don't you endow these intervals with an structure? I mean, this is a set of things, but you can endow them with an algebraic structure, and then you have the dual numbers, and then you are looking at the individual counterpoint in the intervals. Right? I mean, here simply you are pasting two voices. That's the whole of it. And it's revealed in the way that you only are evaluating one point and another point, two voices. And then it comes a very nice thing about what I write about counterpoint. And what is that now is a point. And it's exactly the same viewpoint of Gauss and Sachs. That interval is a point. So you can now move the point is not this point against this point, but this point against this point, and against this point, and against this point. Yes?
And you should have, this was the original understanding of counterpoint.
Exactly.
Counterpoint was not this counters versus counters fields, but it was this kind of sequence of intervals.
Exactly. Before the Garlandia's revolution, I would say, that would be a original meaning. I mean, a point against point. An interval against another interval. And it's so strange because I understood this, I like to say this, I understood this when I exposed like this, the material. I remember writing in the preface of my master's thesis that I was talking about this, but I was saying just like in intuitive understanding, but not in this understanding. By my PhD I was already aware of this. I hadn't wrote it in a formal way, but it was, well, it's a point in space, of course, the intervals. So if you move from zero address to self-address, and here again in zero address, what is the natural next step? Self-address, right? So I have to erase this. So now we have self-addressed points, and these are counterpoint symmetries. Well, no, not all of it. Oh, counterpoint symmetries live within there. But of course, here are many errors. Some are not invertible. But Mazzola asked us to look at the invertible ones that satisfy some axioms that are reasonable for counterpoint rule. And there are some people say, and I think this is Moscow guy, I think they're out of the blue. But Burgaki hasn't read Garlandia's treatise that says consonances. I suppose I have read Sachs, but he doesn't quote Garlandia explicitly, but Garlandia says that the consonance, the nature of an interval depends on its position within the whole things. So you can have something that is consonant, but it's relatively dissonant to the next step. So how do you formalize that? Through counterpoint symmetry. You deform the consonances. So this what is a consonance of fifth minor third. But if you deform it, it becomes a dissonance. And this dissonance has to be resolved. Where? To a consonance that is also at the form consonance as well. So you have to solve this tension. And as far as I understand, the Landia is not talking about perfect and imperfect. But just say that it depends on the position, on the sequence of the counterpoint. And it turned out well, and as far as we have tested it against real music and the neurobiological EEG tests, it works. It's working. But of course, we need more experiments and we need to do more analysis. But it works out well. The more recent thing I have been working in, it turns out that if you have invertible counterpoint, double counterpoint, it turns out that those symmetries, you can have between these 2 points a lot of symmetries. Well, not a lot, at most 5 in the classical setting. But it turns out that when there are few counterpoint symmetries, it's easier to invert the intervals. It's quite to me, it's sort of expected, but I'm surprised that it seems natural. Because I remember talking with Alejandro Nieto, I was explaining him this, and he said, well, to me it sounds like you were saying that the forces, this is a force, this can be conceptualized as a force, dissipates among more symmetries. So if you have less symmetries, the symmetries are like stronger, and in intuitive understanding, they are more capable of supporting this operation of turning them over, right? Well, inverting them. And well, I think this is pretty much the thing I wanted to say. But, yeah, but I just quickly...
We can discuss a bit more what's on the right side of the board. Because there's actually a lot going on here. Yeah, so C12 at C12, the isomorphic C12 epsilon. Is that isomorphism rings? What kind of isomorphism?
Well, no, perhaps I should go here and knowing it with an algebra structure. It would be a much better description of what I have done.
Well, but on the left side, you have some operation. You have coefficient compositions, like endomorphisms.
Yeah, exactly. Yes.
And you can add them.
You can. Addition works well, but the problems and multiplication has to be defined in a non-natural way. But it's not entirely natural because, for example, it says that the tangent space is the same as seeing the dual numbers on the. I can't recall, but it's seeing dual numbers as a generalized space. So that's why I suppose that the inspiration to say, of course, addition is standard addition. You add the linear parts and the fine parts. But you have to define differently the multiplication.
The multiplication is not.
It's not the
addition of endomorphisms?
No.
Endomorphisms?
No, it's not. It is not. You have to define it differently. But I think as a set, it's the same thing. But algebraically, it's not, of course, it's not the same. You have to say it. I say these seeing a set are the same thing. Right? That's what I was saying when I wrote the assembly.
Is epsilon squared 0?
So, yeah.
Epsilon squared is 0.
Yeah.
It's the dual numbers.
The dual numbers.
So what does epsilon correspond to on the left-hand side?
Here?
Yeah.
Well, this one would be this would be x plus epsilon 1. Sets are the same, but of course algebraically they are not the same. But they're the same in some parts of it. There is a beautiful community square in the top of the basic when it says precisely where they are exactly the same thing.
So epsilon is transposition by 1?
No, epsilon is the same as epsilon squared in the
So that's where it fails. I mean, there is no epsilon square equals 0 to the left side.
No. You add that.
But I mean, so on the right, it's a polynomial ring.
Sorry.
On the right, it's a polynomial ring modulo x epsilon.
Yeah, exactly.
So under this correspondence, epsilon would be transposition by 1, according to what you just wrote, x plus epsilon y. So if x is 0, y is 1. That's epsilon. Is it x?
No,
X
not
is
quite,
zero?
but I can't recall
X is
at this
zero.
moment what the precise. It doesn't work out well in equalities. I mean, you cannot algebraically say this corresponds to this. Not
But
in
if there's a
the
bijection.
yeah, there's a bijection of sets.
Yeah, of sets.
Yeah.
You just wrote it down. So x plus epsilon y. So y corresponds to the
Distance.
part.
So the distance between the expertness and this kind of.
But you can also state it algebraically, the C12 to C12 has a linear part, a translation.
Yeah.
It has a multiplication and it has a translation.
Yes, that's what I'm talking about.
And these two components are elements of C12, and you find them again in the polynomial expression A plus epsilon B, and A and B are those two.
Right, that's what I'm getting at.
Yeah, that's it, yes.
So epsilon, if A plus epsilon b, when b is 1 and a is 0.
Yes.
Which map is it?
This is the identity.
That's the identity.
Yes.
Okay.
Well, I just would like to finish that this could be also zero at again. I mean, this is space, and I'm seeing counterpoint symmetries as points, and then you see what the next point, the next thing, taking two counterpoint symmetries and look at a covariant map,
Yes.
and that's what visible works. So
Well, I think we
yeah,
perhaps we should take
you have to.
over again.
And that's what I'm thinking. And the next one would how would it be? Could be transformed more visible work, and go in black and blue. Well, I'm done. So tomorrow we'll talk about someone somewhat different, but it's very related. It's that gestures, and well,
Maybe we can eat a little bit more of an often mathematical music theory. Eat.
yeah. Oh yeah. So
That's why I dropped those things. Yes, dessert.